Algebraic structures, lecture 19, Galois correspondence. Let us start by recalling what we did in the previous lectures. Let F be an algebraic field extension of K. Recall that this extension is called a Galois extension, provided that the following two conditions are satisfied. First of all, this extension is separable, which means that the minimal polynomial over the smaller field for every element in the bigger field shouldn't have multiple roots. And the second condition is that this extension is normal. This means that any irreducible polynomial over K over the smaller field, which has a root in a bigger field, must split over this bigger field into a product of linear factors. Then we have the automorphism group of this extension, and this group consists of all automorphisms of the bigger field which fix the elements of the smaller field pointwise. If our extension is a Galois extension, then this automorphism group is called the Galois group of this extension and denoted the Galois group of F over K. And the major result about finite Galois extensions is the following theorem, which is usually called Artin's theorem. So let K inside F be a finite field extension. Then the following conditions are equivalent. Condition 1, this extension is a Galois extension. Condition 2, F is the splitting field of a polynomial over K, such that all irreducible factors of this polynomial are separable. The third condition, the degree of F over K equals the cardinality of the automorphism group of F over K. Condition 4, the smaller field K coincides with the subfield of fixed points for some finite subgroup G of automorphisms of F. And condition 5, the smaller field K coincides with the subfield of fixed points for the group of all automorphisms of F over K. So this theorem was proved during the last lectures. Now we go further and discuss the subgroups of the automorphism groups as compared to intermediate subfields. So let K inside F be a finite field extension. To each subgroup H of the automorphism group of F over K, we can associate its field of fixed points, so F upper H, and this is the set of all elements in F which are fixed by all elements in H. That's the subfield of fixed points, and this is an intermediate subfield for this extension. This field contains K, and it is contained in F. So this is an intermediate subfield. Conversely, to each intermediate subfield L between K and F, we can associate the subgroup of the automorphism group of F over K, which consists of all elements that fixed all elements in L pointwise. So this subgroup is usually denoted by out F over K sub L. Here are some examples. The set of fixed points for the identity for the trivial subgroup consisting just of the identity, of course, coincides with the bigger field F. Example 2. The subfield of the fixed points for the whole automorphism group of F over K coincides with K if and only if our extension is a Galois extension. So that's one of the statements in Artin's theorem. Example 3. If we take as an intermediate subfield the bigger subfield F, then the subgroup of out F over K, which fixes F pointwise, coincides with the identity subgroup, the trivial subgroup. And example 4. If we take as our intermediate subfield the smaller field K, then the subgroup of out F over K, which fixes all elements of K, will be the whole group of automorphisms of F over K, regardless of whether the extension is a Galois extension or not. This just follows from the definitions. Now we can formulate our main result for today, which is usually called the fundamental theorem of Galois theory, and this is usually attributed to Évariste Galois, who proved some version of it in 1830. So let K inside F be a finite Galois extension. Then the maps which take a subgroup H of the Galois group of F over K and map it to the subfield of fixed points F upper H. And the second map which takes an intermediate subfield L and maps it to the subgroup of the Galois group, which consists of all elements which fix L pointwise. So these two maps between the subgroups of the Galois group and intermediate subfields of our extensions are mutually inverse and even inclusion reversing bijections between the partially ordered sets of subgroups and the partially ordered set of intermediate subfields. So here the partial order is given by inclusion. Moreover, for any intermediate subfield L, the extension of L inside F is a Galois extension, and its Galois group is exactly the subgroup of the Galois group of F over K, which consists of all elements that fix L pointwise. Additionally, the extension of K inside L is a Galois extension if and only if this subgroup Gal F over K sub L is a normal subgroup of the big Galois group, and if this is the case, then the Galois group of L over K is isomorphic to the quotient of the big Galois group by this normal subgroup. Let us now start with the proof of this theorem. So let K inside F be a finite Galois extension. We start with an easy observation that if H and K are two subgroups of the Galois group, which are embedded into each other, then certainly the corresponding intermediate subfields of fixed points are embedded in the opposite way. So the bigger the group, the smaller amount of points it fixes. Similarly, if we have two intermediate subfields K and L of this extension which are embedded into each other, then the corresponding stabilizer subgroups are also embedded in the opposite way. The bigger the subfield, the less elements of the Galois group fix it. So this means that our two maps, which associates to a subgroup its subfield of fixed points, and to a subfield its stabilizer subgroup, are inclusion reversing. Next, the fact that the extension of K inside F is a Galois extension means that F is a splitting field of some polynomial f of x over K, whose all irreducible factors are separable. But then we can consider the same polynomial as a polynomial over L, and so F remains a splitting field of the same polynomial. And then, of course, this means that the extension of L inside F for any intermediate subfield L is a Galois extension by Artin's theorem. In particular, by Artin's theorem, L coincides with the set of fixed points for its stabilizer subgroup, and also by Artin's theorem, the Galois group of F over L is exactly the stabilizer subgroup of L inside the Galois group of F over K. Next, if H is a subgroup of the Galois group of F over K, then the set of fixed points for H is a Galois extension, again by Artin's theorem, and so by Artin's theorem H coincides with the Galois group of F over the set of fixed points. And this implies that our two maps, subgroup to the set of fixed points, subfield to its stabilizer subgroup, are mutually inverse bijections. So it remains to prove the claims about the extension of a smaller field to the intermediate subfield. So first of all, the extension of K inside L is separable because L is an intermediate subfield of a separable extension. This extension is normal if and only if, for any further finite extension of L into some k, any automorphism of k that fixes k pointwise sends L to L. This was our characterization of normal extensions. Using the statement about extension of field homomorphisms, we may assume that k contains f. Since the extension of little k to f is normal, any automorphism of bigger k which fixes k pointwise sends f to f. Therefore, the extension of k to L is normal if and only if any element of the Galois group of f over k sends L to L. So, let us first assume that for any element A in L and any element sigma in the big Galois group, sigma of A belongs to L. Let tau be an element in the stabilizer subgroup of L in the big Galois group. Then sigma inverse of tau of sigma of A is equal to A, because sigma of A is in L, tau fixes it, and so sigma inverse of sigma of A is A. And of course this means that sigma inverse tau sigma belongs to the stabilizer subgroup. And this means exactly that the stabilizer subgroup is normal in the big Galois group. So if you take an element from the subgroup and conjugate it by anything in the big Galois group, we stay in the subgroup. That's exactly normality of the subgroup. So now we have proved our claim in one direction. Conversely, assume that the stabilizer subgroup is normal in the big Galois group. So this means that for any sigma in the big Galois group and any tau in the stabilizer subgroup, sigma inverse tau sigma belongs to the stabilizer subgroup. Given an element A in L, we have that sigma inverse of tau of sigma of A is equal to A. That's because sigma inverse tau sigma belongs to the stabilizer subgroup. If we apply sigma, we get tau of sigma of A is equal to sigma of A, and this holds for any tau in our stabilizer subgroup. And so by Artin's theorem, it means that sigma of A belongs to L. Okay, so we have now proved that the extension of k inside L is normal if and only if the corresponding stabilizer subgroup is normal in the big Galois group. It remains to identify the Galois group of this smaller extension in the case when the extension is normal. So let's now assume that this extension is normal. By extension of homomorphisms property, any element of this smaller Galois group can be extended to an element of a bigger Galois group. Moreover, since the extension is normal, we know that any element of the bigger Galois group restricts to an element of a smaller Galois group. Therefore, restriction provides a surjective homomorphism from the bigger Galois group to the smaller Galois group. By definition, the kernel of this homomorphism is exactly the stabilizer subgroup, and so we get from the first isomorphism theorem that the smaller Galois group is isomorphic to the bigger Galois group modulo the stabilizer subgroup. And this completes the proof of the fundamental theorem of Galois theory. Let us illustrate it on one explicit example. Example: consider the field extension of rational numbers into the field which is obtained from rational numbers by adding the element the square root of 2 plus the square root of 3. We have already seen before that this field, when we add the square root of 2 plus the square root of 3, is the same thing that we get if we add to rational numbers both the square root of 2 and the square root of 3. So the extension of q inside q with the square root of 2 and the square root of 3 added is separable because we are in characteristic 0. The minimal polynomial of the square root of 2 is x squared minus 2, and the other root of the x squared minus 2 is minus the square root of 2, and of course it also belongs to our big field. The minimal polynomial of the square root of 3 is x squared minus 3. The other root of this polynomial is minus the square root of 3, and it also belongs to our bigger field. This means that our bigger field is the splitting field of the polynomial x squared minus 2 times x squared minus 3, and so our extension is normal. So our extension is a Galois extension because it is both separable and normal. So let us determine the Galois group. Let us start by determining the dimension of our bigger field over the smaller field. As a first step, consider the extension of rational numbers, two rational numbers with the square root of 2 added. So the minimal polynomial of the square root of 2 is x squared minus 2. It has degree 2. And so we have that when we add the square root of 2, the dimension of the bigger field over the smaller field will be 2. And also the elements 1 and the square root of 2 will form a basis of the bigger field over the smaller field. Next, consider the extension when we add to q with the square root of 2 added, the elements the square root of 3. We know that the square root of 3 doesn't belong to q with the square root of 2 added, and therefore this extension from q with the square root of 2 to q with the square root of 2 and the square root of 3 is non-trivial. And therefore the minimal polynomial of the square root of 3 over q with the square root of 2 added is x squared minus 3. And this implies that the extension of this bigger field over q with the square root of 2 added is also 2. And that the elements 1 and the square root of 3 form a basis of the bigger field over the smaller field. So now by transitivity, so we first extended q by the square root of 2, and then also by the square root of 3. In both cases we had extension of degree 2. By transitivity, the extension from q to the q with both elements added has degree 4. And as a basis, we should take the product of the two bases which we got before. So we get 1, the square root of 2, the square root of 3, and the square root of 6, which is the product of the square root of 2 and the square root of 3. So these four elements form a basis over our bigger field over Q. And this implies that the Galois group of our bigger field over Q has 4 elements. So each element sigma in this Galois group sends the square root of 2 to either the square root of 2 or minus the square root of 2, because these two elements are the two roots of x squared minus 2. And this polynomial with rational coefficients is fixed by sigma. Also, similarly, sigma sends the square root of 3 to plus or minus the square root of 3, because these are the roots of x squared minus 3, which is fixed by sigma. Note that we know that if we know what the element sigma does to the square root of 2 and the square root of 3, we know what it does to the product of these two elements, because sigma is an automorphism. And that's exactly the element the square root of 6, the fourth element in our basis. And of course, any automorphism sends 1 to 1. So this means that the values of sigma at the square root of 2 and the square root of 3 determine sigma uniquely. So this gives at most 4 possibilities for sigma. So we have 2 choices for the value at the square root of 2 and 2 choices for the value at the square root of 3. Since we know that the Galois group does have 4 elements, all these 4 possibilities are realizable, so they give us 4 different elements in our big Galois group. So we have the following elements in the Galois group. The identity element, it sends the square root of 2 to the square root of 2 and the square root of 3 to the square root of 3. The element which we denote by sigma, which sends the square root of 2 to minus the square root of 2 and the square root of 3 to the square root of 3. The element which we denote by tau, it sends the square root of 2 to the square root of 2 and the square root of 3 to minus the square root of 3. And the element which we denote by omega, which sends the square root of 2 to minus the square root of 2 and the square root of 3 to minus the square root of 3. And now from this datum we can compute the Cayley table for the Galois group by just looking at what the elements do on the square root of 2 and the square root of 3. We have the following table. Of course, the identity multiplies as the identity. So sigma squared, tau squared, and omega squared are the identities. And then sigma tau is omega, sigma omega is tau, tau sigma is omega, tau omega is sigma, omega sigma is tau, and omega tau is sigma. And from the Cayley table, we in particular see that all elements in this group have order 2. The group itself has 4 elements, and there are 2 groups with 4 elements, Z4 and Z2 times Z2. The difference between these 2 groups is that Z4 has an element of order 4, while all non-identity elements in Z2 times Z2 have order 2. And in our case, we see that in our Galois group, all non-identity elements have order 2. Therefore, our Galois group is isomorphic to Z2 times Z2. The group Z2 times Z2 has 5 subgroups. The trivial subgroup with the identity, the whole group as a subgroup, and then we have 3 subgroups which contain the identity and one of the 3 elements of order 2. So each such subgroup has 2 elements. And here is the posets of subgroups of our Galois groups with respect to inclusions. So we have the smallest subgroup, the identity, the largest subgroup is the whole group, and here in the middle we have 3 two-element subgroups, each consisting of the identity and one of the elements of order 2. So now we can use our main theorem to describe the poset of intermediate subfields for our extensions. So we just take this poset, reverse it, and write as an upper symbol to our big field, Q with the square root of 2 and the square root of 3 added. So what we get is the following picture. So the smallest subfield is a fixed subfield for the whole group, the largest is a fixed subfield for the identity, and here in the middle we have 3 subfields for each of the 2-element subgroups. And now we can determine all these subfields very concretely. So the field, which is stabilized just by the identity, is the big field. The field which is stabilized by the whole Galois group is a small field, which is rational numbers. That's because we have a Galois extension. The field which is stabilized by the subgroup which contains sigma is of course Q with the square root of 3 added, because sigma of square root of 3 is equal to the square root of 3. The intermediate subfield, which is stabilized by the 2-element subgroup which contains tau, is Q with the square root of 2 added, because tau of the square root of 2 is equal to the square root of 2. And the fixed subfield for the subgroup with omega is Q with the square root of 6, because omega fixes the square root of 6. So omega changes sign for the square root of 2, and it changes sign for the square root of 3. But then it means that it fixes the square root of 6. And of course, all proper intermediate subfields have degree 2 over Q. And also, since our big Galois group is abelian, all subgroups are normal, so all intermediate subfields are Galois extensions of the rational numbers. And here is the concrete diagram of the poset of intermediate subfields of our Galois extension. So our smallest field is Q, our largest field is Q with both the square root of 2 and the square root of 3 added, and in between we have Q with the square root of 3 added, we have Q with the square root of 2 added, and we have Q with the square root of 6 added. And the important information is there are no other intermediate subfields. That's the complete picture. Some additional problems and questions at the end. Problem question 1. Let K inside F be a finite field extension and H a subgroup of the automorphism group of F over K. Prove that the fixed field of H coincides with the fixed field for the stabilizer subgroup of the automorphism group for the fixed field of F over H. Problem question 2. Let K inside F be a finite field extension and L an intermediate subfield. Prove that the stabilizer subgroup for L coincides with the stabilizer subgroup for the subfield, which is the fixed field for the stabilizer subgroup of L. Problem question 3. Let K inside F be a finite field extension. Prove that the map which takes the subgroup and sends it to the stabilizer subfield is injective. Problem question 4. Let K inside F be a finite field extension. Prove that the map which takes an intermediate subfield and sends it to the stabilizer subgroup is surjective. So note that in these 4 questions we do not assume that the extension is a Galois extension. And problem question 5. Determine the Galois group and all intermediate subfields for the field extension of Q inside Q with the element the square root of 2 plus the square root of 3 plus the square root of 5 added. Thank you very much and see you next time.